We train AI to write code, we train AI to generate images, we train AI to predict the stock market. But what happens when you point a neural network at the actual laws of the universe, and it finds ones we missed? Researchers at Emory University just published a paper in PNAS, one of the most respected scientific journals on Earth, showing that an AI discovered previously unknown physics in the fourth state of matter. Not solid, not liquid, not gas. Plasma. Specifically, dusty plasma, the kind that forms during wildfires and can knock out emergency radio communications. Classical physics said we understood how charged dust particles interact. We were wrong, and a neural network proved it. Okay, quick physics crash course. Most people know three states of matter: solid, liquid, gas. But there's a fourth one that makes up over 99% of the visible universe. Plasma is what you get when you heat a gas so much that electrons start ripping away from atoms. You end up with a soup of charged particles, ions and free electrons. Stars are plasma. Lightning is plasma. The inside of a neon sign is plasma. Now, dusty plasma is plasma with a twist. Take regular plasma and add tiny solid particles, dust grains, a few micrometers across. These grains pick up electrical charges from the surrounding plasma, and they start interacting in complicated ways. They form crystal structures, fluid-like flows, and wave patterns. Where do you actually find dusty plasma? Saturn's rings, comet tails, interstellar clouds. And here's the one that matters on Earth: wildfires. When soot and ash particles mix with the superheated ionized air above a wildfire, you get dusty plasma. And that dusty plasma can scatter and absorb radio frequencies, disrupting communication for firefighters in the field. Understanding how dusty plasma actually works isn't just academic. It has real consequences for people on the ground. So here's what the Emory team did. They built an experiment where they could create dusty plasma under controlled conditions and track every single particle in 3 dimensions. They know the position, velocity, and trajectory of each dust grain at every moment. But tracking particles is the easy part. The hard part is figuring out the forces between them. Classical theory says dust particle charge is a function of particle size. Bigger particle, more charge. Simple. That's been the model for decades. The researchers fed their 3D particle tracking data into a custom neural network, not a general-purpose language model, a purpose-built architecture designed to learn the equations of motion governing the system. The AI's job was to figure out the actual forces at play by watching how particles move and interact, and the neural network found something the textbooks got wrong. Dust particle charge doesn't just depend on size, it depends on the surrounding plasma density and temperature. The charge is dynamic. It shifts as local conditions change. Classical theory treated it as static. The AI found it's anything but. The model achieved over 99% accuracy in describing the non-reciprocal forces between dust grains. Non-reciprocal means that particle A pushes on particle B with a different force than B pushes back on A. Newton's third law, equal and opposite reactions, doesn't cleanly apply here because the plasma medium itself mediates the interaction asymmetrically. That's not a minor correction. That's a fundamental gap in the theoretical framework we've been using for decades. Now, you might be thinking, cool, dusty plasma physics got an update. Why should anyone outside a physics lab care? 3 reasons. First, the wildfire problem. If we don't correctly model how dusty plasma absorbs and scatters radio waves, we can't build reliable communication systems for firefighters. Every fire season, crews lose radio contact in critical moments. Better plasma models could save lives. Second, space exploration. Dusty plasma is everywhere in space. It coats spacecraft, interferes with instruments, and affects how we design everything from solar panels to Mars landers. Getting the physics right matters for every mission we send out. But the third reason is the big one. This isn't just a story about plasma. It's a story about what AI can do for science. This neural network didn't just analyze data faster than a human could. It discovered a physical law that humans had gotten wrong for decades. It looked at the raw motion of particles and said, "Your model is incomplete. Here's what you're missing." That's a qualitative leap. We've gone from AI as a tool that helps scientists crunch numbers to AI as a tool that can identify gaps in human understanding and fill them. The PNAS publication is peer-reviewed validation that this approach works. And the Emory team isn't alone. In the last year, AI systems have discovered new antibiotics, predicted protein structures, and found patterns in astronomical data that humans missed. But finding a missing term in the fundamental equations of motion of a physical system? That's different. That's AI doing theoretical physics. Here's what keeps me up at night about this. We've been using the same theoretical framework for dusty plasma since the 1990s. Thousands of papers have been published using those equations. Experiments have been designed around those assumptions. And a neural network just showed that a key variable was treated as constant when it should have been dynamic. How many other fields have the same problem? How many areas of physics, chemistry, biology, and engineering are built on models that are close enough to work most of the time, but fundamentally incomplete. Because if a neural network can find missing physics in plasma, it can find missing physics everywhere. Every field with high-quality experimental data and established theoretical models is now a candidate for AI-driven discovery. Material science, fluid dynamics, quantum systems, climate modeling. We spent decades training AI to do human tasks: write, draw, code, chat. It turns out the most important thing AI might do is the thing humans can't. Look at the universe with no assumptions and find the patterns we were too biased to see. The Emory team's paper was published in the Proceedings of the National Academy of Sciences this week. The neural network, the methodology, and the corrected plasma models are all there. Peer-reviewed, reproducible, real. And AI just found physics we missed, and it probably won't be the last time. That's it for today. If this story blew your mind even a little bit, hit subscribe. We cover stories like this every single day. The intersection of AI and science is moving faster than anyone expected, and I don't want you to miss what comes next. I'll see you tomorrow.